start this recording. And all right, we're ready. We're ready. Fresh week. What I've done is I made a copy of those overall slides that we're working our way through and then removed the stuff from last day, so it'll kind of start fresh. But just as a reminder, we'll do a little bit of review, but I just kept the last slide that we finished on and like just finished on. Okay. And I guess I could have put this review page, but this is, I knew it felt like a long time ago. It's from Wednesday. It's crazy. So this is from last day. The variance is where we ended off. And we were talking about variance as a measure of spread, right? And there are a couple of issues with using the variance. One of the main ones being that the units for variance are the units squared, which is kind of hard to talk about, right? And so that's why we'll introduce, or that's not why, but that's one of the reasons we'll introduce the standard deviation as a measure of spread instead. So as a little bit of review, oops, didn't pick up from last week, right? We said to describe any distribution, right? We need to talk about three things: shape, center, and spread, right? And so to describe any distribution, we need to discuss one, shape, two, center, and three, spread. In terms of the shape, first we talked about modality, right? How many modes, right? Unimodal, bimodal, multimodal, modes being how many peaks do you have, right? And so first we said, okay, modes, right? Typically we're focusing on unimodal distributions, right? And so we can talk about modes and we can also talk about skew. Now, usually I would review skew, but for today, because we're going to talk about it again, I just want to remind you that something like this is skewed to the right, or positive skew, because it's always skewed in the direction of the tail. And so here, this is a right skew. And something like this would be a left skew. Which, I don't know, to me, that's counterintuitive. I don't know. So it's worth remembering, right? It's skewed in the direction of the tail. And we'll see a little bit more why that might be today. And then we didn't get very far, but we did introduce one measure of center being the average, right? And so we can kind of eyeball the center from a graph or a histogram, or we can calculate the center, right? And so one of those centers we introduced was the mean. Right? The mean is a calculated measure of center. And that's where the variance comes in, right? The variance is a calculated measure of spread. Okay. And the variance is a calculated measure of spread. We're going to introduce a couple more today. So we'll have a few more up our sleeves. And wouldn't you know it, it comes down to what shape we have. right? So the shape of the distribution is gonna tell us what the appropriate measures of center and spread are. Okay. We will see today that the shape of the distribution will determine the appropriate measure of center and spread. Will determine the appropriate measure of center and spread. Yeah. And now I'm having that panicky moment. Did I record or was I just, oh, phew. It is the worst feeling when I realize that I was not recording. It's only happened a few times, but. Yeah. All right. So we'll call it, it's kind of a segue into today, not really a review necessarily, but it was like a previously on Stat 124, the things you need to know. There were other things last week. So, okay, this is why, and I'm gonna try to put this page up top later, but for now, let's just talk about the variance again, just review the variance, I guess. And so we broke it down last day and we said, okay, each observation xi, right? x1, x2, x3, x4, right? What I do is I look at the distance from the mean. Remember, the mean is denoted by x bar. Anything with a bar over it is a sample mean. So now I'm seeing how far are you from the average, right? And then what do? Then I square each of those distances, and we'll talk about why. Okay. But just as a fact, we square them. What does that do? Makes negative distances positive, right? And so that's a bonus when you're adding things up. Otherwise, they just add to 0, right? Just because of, is that a door? Because of how the average works, they would just add to 0, right? So that's a fact. So then we square them, ditch the negatives, right? And then we can add those all up. So now we have the sum of the squared deviations from the mean, right? And then we divide by n minus 1. We don't need to worry about y, just as long as we remember that we do, right? It'll be on a formula sheet, so yeah.
At the 5, the 9, and the 7, I'm assuming those are like powers of sleep.
Yeah, those would be the observed values, totally. So it's tough because for this example, they don't show us the data set. I guess we could figure it out from here, but that's a lot of work that we don't need to do, right? But these are the observed hours of sleep, right? And the 6.71 is the sample mean. And so we square those, add them all up, and then bada boom, bada bing, we're at 4.11-ish hours. Squared variance. Hard to talk about, hard to think about, in my opinion. Maybe you guys think about squares all the time, I don't know. So the question is, why would we use the squares? Well, there's the obvious, right? Making it positive, something like that. So that's the number one reason, okay? But also another kind of benefit is that if we take, for example, a distance of 1, right? If the deviation is 1, the deviation being x minus x bar, right? That's the deviation. If that distance is 1, meaning the observation is 1 unit above the mean, then the squared deviation, so the deviation squared, which is x minus x bar squared, which is what we're doing, becomes what? Well, it becomes 1, right? 1 squared is 1. What if we double that deviation to 2, right? What if we say, okay, this deviation is now 2. This observation is 2 units away from the mean, above the mean. Now, all of a sudden, the squared deviation is 4, right? Which means that we're amplifying these larger distances, right? And kind of increasing the spread that way, or communicating the increase in spread that way. Okay? And so here, I like to think of it as we amplify larger distances instead of just saying the squared deviation is, right? It's not linear anymore. It's 1 goes to 1, but 2 goes to 4, 3 goes to 9, and it kind of explodes. Right? So we're penalized for those large distances. Okay. So along those lines, we have the standard deviation. Now the standard deviation relies on the variance. It's just the square root of the variance. Yeah. And so here, S is the square root of the variance. If you prefer to see it that way, we did denote the variance as S squared, right? Which means if I take the square root of it, I get to S, okay, which is what we use to denote the standard deviation. Now, maybe now is a good time to introduce kind of confusing notation. If it's a calculated value, we use a lowercase s for the sample standard deviation. Okay. And so here, S is the sample standard deviation. And I'll put in brackets the calculated value. But you also don't want to be writing standard deviation all the time when you're writing notes, right? So then we use SD, capital S usually, capital SD is the standard deviation. Bless you. Abbreviation. I guess I think it's maybe a little bit confusing because why not just use the same thing? But we don't. Okay, let's see here. So if we take the square root of 4.11, now notice here, right? It's also the square root of the hours squared. Right, we take the square root of the units as well. And so that's why we're back to just plain hours. And that's nice to talk about, right? Centered on 6.71 hours of sleep with a spread of 2.03 hours. Now the spread isn't the entire spread anymore. Okay? It's gonna be, just as a rule, or kind of a little fun fact, an LFF, I guess, is that all the data are typically within 3 standard deviations of the mean. Okay? I'll call this I like to call it a little fun fact. Still a fact, so it's still important, but it's a fun one. Sometimes we'll have a few data points that are outside. Have you heard of like 6 sigma, that kind of thing? It's like a, I don't know, efficiency processor, I don't know. But this is what it's based off of. All the data is within 3 standard deviations of the mean on either side, right? And so, and we'll see that more, but that's something to keep in mind for later. Now, It's hard because I want to be standing up and showing you, but it's really hard to write standing hunched over. I'll do a little bit of both. Okay. I feel like a dental hygienist. All right, let's see what we got here. You need to floss more. All right. So what's another measure of center that we could talk about? Another measure of center that we could have is the median. Now, the median is just the value or the data point that splits your data in half. Okay. Nothing too crazy. And what do we have to do if we want to split our data in half? Well, we have to sort it first. Okay, so step number one here is step one, sort your data from smallest to largest. I mean, you could go the other way, but that would be weird to me. There's nothing wrong with that though. Wow, that'd be hard to do for me, but maybe you can do it. So then if the median is the value that splits your data in half, once you have your data sorted, right, just like here, 0, 1, 2, 3, 4, what do? I like to use my my patent pending boop, boop, boop method. You just take your fingers. We're only going to do this with small data sets, obviously, otherwise you'll go cross-eyed. But what do? You just boop, 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 boop. But I do it simultaneously. Boop, boop, boop. And then you land on the middle value. There are formulas and things that we could use to find the location, but because we're going to be using maybe maximum 15 data points, you can just boop, 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 find the middle value. Okay. Now, if you have an even number of observations, what's going to happen, right? If you are, and I'll boop, boop, boop here on the screen, boop, boop, you land on 2 and 3 at the same time, right? So usually how we denote it, it's not a huge deal, but I like to circle them and draw a line through it just to show that the median is actually neither of those values. The median this is where it gets a little bit wild. The median is the average of those two numbers, 2.5. Wait, I thought the median was the central value. It is, but if you land on 2 central values, then you take the average. They're all linked. Okay. So now, I guess the main thing to recognize here, and this is just for future calculations, because we're going to do it for the what we call the quartiles as well, where we split it into quarters, not just halves. So then it's going to be important to remember that if you use the middle or the average as the median, neither of these values are the median, right? They contributed to it, but it means that neither of these are the median, right? The median is 2.5, so neither of those. So what we can do, there's lots of different terminology that we could use, but the median, since it's the midpoint, we could also call it the 50th percentile. The percentile meaning it has that percent of the data below it. Okay. And so here the percentile is, so the, I'll say the nth percentile has n% of the data below it. I'm back to standing, I guess. It's short-lived. the power of the rolly chair. What are some other percentiles that we could talk about? So the most common things that we do are finding the 25th percentile, the 75th percentile, along with the 50th. Now we've cut it all into quarters, right? And so those are common percentiles that we find. Okay, so the 25th percentile is also called the first quartile, right? The first quarter of the data, okay, which we denote by Q1 traditionally. Usually it's a Q subscript 1, so, oh well. But I guess that's nice too. And then, of course, the 50th percentile is the median. You could call it, if you know you want to get wild here, you could call the median Q2, right? Nothing wrong with that. It is the second quarter, right? 75th percentile is called the third quartile, Q3. Yeah. And between Q1 and Q3 is the central 50% of your data, right? And so what we call that, we give it a special name called the interquartile range, because we use it to do some calculations later. But it's really just, if you want the distance between Q1 and Q3, Q3 is always bigger, right? So distances have to be positive. So you take Q3 minus Q1. Otherwise, you have to deal with a negative. Okay. So the interquartile range is the distance between Q1 and Q3. Let's see here. Okay. If we have some values, just quickly, because I think, sorry, let me just, don't look, okay? No, you can look. Okay. I'll come up with some values. I'm gonna pre-sort them. So I'll start with 7, 9, no creativity, 11, 12, 15, 17, 20, 22, 1, 2, 3, 4, 5, 6, 7, 8.
What? I don't care. Shut up.
I have to assume that wasn't for here. Gonna mute everyone. There. Don't worry. It's pretty funny. That's fair. That's fair. All right. So just quickly, I'm gonna do it with 8 values, but also I'm going to tack on another set or another value here. I'll just throw on 25. Then we can see how to do these just quick and dirty. Of course, you would use Excel to find these for anything bigger, right? It's already filling our page, a little bit crazy. All right, so the first thing you're gonna wanna do is to sort your data, obviously, but we've already done that. Okay. Or I already did that. Then what we're gonna do is you're going to find the median, right? So step number 1, I'll put it on here, sort. Step number 2, median. You need to find the midpoint in order to cut it up further into quarters. Now I'm gonna sit down. All right, because I'm gonna take my fingers, my trusty digits, and boop, 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 all the way to the center. And so here we go. Boop, boop, boop. I landed on there. Sometimes because it's hard to see, I like to just confirm that I have an even number of values on either side. But because I landed on 2 values here, the median is going to be 12 plus 15 divided by 2. Heck if I know. Sold. 13 and a half. Math, who needs it? No, I don't do mental math, so it's okay. It's okay not to. All right, so now, like I was saying, the important part is to recognize that this line is the median. Okay, so when we're counting in, we start at the 12. Okay, and the difference is going to be later, if we've used the value, then we don't use it to count in. Right? Subtle differences, and any software that you use, they're going to have slightly different ways of doing it. For example, what you'll find is Excel is going to use a weighted distribution and say, oh, there was quite some distance here, I'll make up for it. So it'll get fancier quartiles than what we do, but this is good enough for us. All right, so 7 and 12, now I'm finding what? The first quartile, right? So boop, boop. Well, the other boop was from the other side. So now Q1 this one I feel like I can handle. Is going to be 10. And depending on the number of observations that you have, right? Sometimes you'll land on a number, sometimes you end up taking the average, right? And so it just depends. And now what can we do? We can find Q3, right? Which is on the other side, splits the top half of the data in half, right? Quarters. And so boop, boop, same deal here. I'll put it up here. Q3, 17 plus 20 divided by 2. 18 and a half. Yeah, that works for me. Thank you. And then, of course, we have, so then, oh, you know what I should do? 3, Q1 and Q3. And the last thing that we might want to know about is the minimum and the maximum, right? Because they're sorted, these are like gimme marks, right? Here, the minimum is 7 and the maximum is 22. These numbers, minimum, Q1, median, Q3, and the maximum are what we call a 5-number summary. Okay. It's hard, but you could take those numbers and kind of visualize the distribution, right? So what does it mean if two values here are close together? It means that a lot of the data points happen in that spread, right? And if there's a long distance between two of these values, right, then it took a long time to cover 25% of the data, right? Yeah.
You have 8 values there. Wouldn't Q1 and Q3 just be 9 and 20? Like, why do you need to take the average?
Because I counted in from 15, for example. So here and here. The alternate, let's do this other one, this alternative here. Okay. Fingers ready. And it's hard because I can't have 2 pointers. So I'm going to do it with 1 pointer. Boop, 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 boop. And change my pen. So now here the median is 15, which means, and if I count, I have 4 observations on either side, so it feels good, right? And so now I can't use this anymore because it's already been used as the median. And so what happens when I find the quartile now, I'm still going to be taking the average here, but from a different route. So here, or kind of by a different route, I guess. So Q1 is 9 plus 11 divided by 2. So kind of an unfortunate example, I think, because they're the same. You can't win them all. And then the third quartile, again, now I've used 15, so I'm not allowed to use it again. So to indicate that, I'm gonna do this. But now Q3 has changed to the average between 20 and 22. Gonna go with 21. Behavior is a little bit different. Is it old school to make you learn this stuff? Yeah, it is, right? Because we have software that just does it. More sophisticated than this, right? But we're checking boxes too. So yeah. Okay. I will say maybe the 5-number summary, because I might ask you for the 5-number summary. Is the minimum, Q1, median, Q3, and the maximum. You want to make sure that you list them in that order, because otherwise it's weird. Doesn't make sense. Right? But you're just working across here. So the reason that I bring that up is because that's a nice way to ask you, hey, do you remember how to find the median and the quartiles, right? And then there's 2 gimme marks here, the minimum and the maximum. Right? Sorry, I really crowded this slide here. I think that's good for there. Any questions before we move on? All right. So a box plot is, I want to say exactly like it sounds. It's a graphical representation of basically the 5-number summary with a little extra. Okay. And so here, the box, so this is what a box plot looks like. Okay. You've got a numerical variable on this axis. Sometimes you can flip it on its side. That's fine too, I guess, but usually we have it like this. Space dependent. That's all. So the box represents the middle 50% of the data. Okay. And so here you have the middle 50% of the data. Starting from the minimum here, right? And we've got the anatomy of the box plot on the next slide, so I'm going to try to not duplicate too much, but just as a heads up, the thick line in the middle shows where the median is. And then, of course, if it's the middle 50% of the data in the box, then this would be Q1 and this would be Q3. So that's where the meat and potatoes are, right? The middle 50% of the data. And then we kind of let things happen on either side. So this is another way that we can visualize numerical variables, right? We had histograms, but box plots allow us to, so we use box plots to visualize numerical variables. The distributions as well. Like I said, short distances mean that there's a lot of data there, right? Which is also, everything is counterintuitive to me, I'm realizing. But I don't know, I find that it is. Initially, if you think about it, it makes sense. Okay, just so we can have this all on one screen here. Here is the anatomy of a box plot. So we already talked about the median, Q1, Q3. Yeah. And then these are called whiskers, which is kind of cute. You can call them fences if you want, but I like whiskers. Just, I don't know, it's cuter. And so we draw these whiskers, but at some point we stop extending them. And there's math behind how far they go that we're going to introduce. Don't worry. Right? But what are those whiskers doing? They're identifying potential outliers, right? Potential data points that are extreme relative to the rest of the data. Okay, so these are suspected outliers. We can have them on the bottom as well, but in this case, we don't. Okay. It's also got the dot plot beside it, just so you can see how they relate, but just focus on the box plot for now. Forever. So those whiskers and outliers, whiskers of a box plot, just as a rule, we tend to use 1.5 times the interquartile range as an allowable distance from the quartiles. Oh boy. Easier if you use mathematical notation, right? So I think this is Tukey's box plot. He used 1.5. There are others that use 2. There's, I'm sure someone has tried to argue 1.7, for example. So the 1.5 is relatively arbitrary, but that's the one that we're sticking to just generally. Okay. So the max upper whisker reach is going to be from Q3. And this is where I find that it's helpful to remember the anatomy of the box plot, right? So you're going from Q3, you're allowed to go 1.5 times the interquartile range, right? Where this is the interquartile range, of course. This distance here is the interquartile range. So this is allowed to be 1.5 times that distance. So the max upper whisker reach is Q3 plus 1.5 times the interquartile range, whereas the lower whisker, right, just visually, now we're going down from Q1. So now we have to do Q1 minus 1.5 times the interquartile range. What's a little bit an added layer, let's call it, is that those whiskers, we can calculate the bounds or the max whisker reaches. For example, if we have an interquartile range of 10, just as an example, then what do we have? We have Q3 must be 20 and Q1 must be 10. Then the range between them is 10, a distance of 10. Okay, so what we're saying is that the max upper whisker reach is allowed to be from 20. I'm allowed to go 1.5 times 10, puts me at 35. Okay. The lower whisker reach, 10, but now I have to go down 1.5 times the interquartile range. So down 15 puts me at -5. Okay. Now this is supposed to match with what's here. And so why isn't this whisker going down to -5, right? This whisker was allowed to go to -5. Let's say that's somewhere here. But what happens is our box plot, so we do all this work, we find the whiskers where they're allowed to go to, and then we only show data points that are actually in the data, right? And so this must be the smallest data point within the lower bound or the lower whisker bound. if you don't have any outliers, right, no values beyond -5, which we don't here, we can see visually, right, then you don't have any outliers or any suspected outliers. Okay. Then this line would just be at the minimum, right? What we see on the top here, though, is that, okay, we've drawn the whisker, it says it's the max whisker reach and the upper whisker, but it should be the smallest, or sorry, the largest value within the bound, right? Because we only draw data points. So here, it's the largest value within the bound, the upper bound. So what happens if you're doing it by hand, which I don't think we should be doing, but if you are, what do you have to do? You have to kind of draw your box plot, draw your whiskers where the bounds are, and then you shorten it or draw outliers, right? The data points that are outside. So you kind of make adjustments as you go. But that's the general anatomy of a box plot. Yeah.
How are those suspected outliers up top determined?
So it's if they are more than 1.5 times the interquartile range away from the third quartile in this case, because they're on the top, then we consider them outliers. So we're allowed to have data points beyond then, but how we indicate that they're really far away from the rest of the data is by using that calculation. The 1.5 IQR rule is often how I refer to it. So that's the rule that we're going to use. And I think the hardest part when you're starting with this stuff is just to keep track of the plus and the minus. But if you visualize it at the same time, then it'll kind of guide you to, okay, from Q1, I have to go down, right? Because otherwise I'm going up and it doesn't make sense. And from Q3, I have to go up, so then I have to add, right? So let the box plot be your guide. I should make t-shirts. Let the box plot be your guide. Someone write that down. No, don't do that. Well, you can. It's pretty funny. Okay, so what we said, right, is that a potential outlier is any observation beyond these whiskers. We look a little bit deeper into them. Are they data entry errors? Are they just observations that are very interesting? That can happen, or that's usually what we're hoping for, right? But in general, they're just extreme relative to the rest of the data, right? So they're going to require a little bit of work. Outliers. Why is it important to look for outliers? Gives us the skew of the distribution, right? So if I'm looking at this box plot here, I'll do a cleaner version. I'll go like that. Smaller. Come on. Okay. When you're just starting, it's really difficult to map this from a box plot to a potential histogram. Can't spell anymore. Can't write either. But what are we going to do? because the histogram looks like this, so it's flipped on the other axis, what's my first step? Well, first thing I'm gonna do is I'm going to rotate this thing. Or maybe I'll keep this and make a copy. Whoops. Copy. Paste. Come on. Rotate. All right. Technology. Yep. And let me see here. There. That worked out well. So now, right, it's saying that I have a lot of data points. 25% of the data is in this tiny little range here, 25, 25, 25. And then between here and here is 25. I guess it ends there. Right, between Q3 and the maximum. And so that's quite a long distance, which gives me that tail, right? So here, if I have to map this out, I'd go like this, right? Because I'm seeing a lot of those data points in that short stretch, which I can show by on the histogram by a huge blob. Technical term, yes. But then it takes me a long time to get to these extreme values. Okay. Nice. All right. So now we have two. This poor soul's trying to get some work done. Outliers. We've got two measures of center, right? The mean and the median. We've got three measures of spread, the variance, which we're kind of forgetting about, standard deviation, and the interquartile range is a measure of spread, right? The central 50% of the data. So if we had to think about how these values are affected by outliers, right? If we have data points like this, and what if we replace, it's hard to tell because they've got these weird scales, but if the largest value is replaced by 10 million, how would that be affecting our centers and spreads, right? If we, and I'm just going to go back to the one that we were working on here. Okay. If we think about it this way, if I change this to 250, right, this last value, I'm going to change it to 250. Would the median change? No, right? It doesn't care, right? Because it just boops, boop, 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 boops in, okay? But if I was to take the mean, the average, all of a sudden changing this from 25 to 250 makes a huge difference, right? And that average would be, or the mean is pulled in the direction of the outliers, right? So the term that we use for that is the median and the interquartile range. They're robust to outliers. Okay, just kind of a fun thing to think about. Whereas the mean and the standard deviation are not robust to outliers because the standard deviation would do the same thing, right? It uses the mean to find the distances, and now the distances are really far, all of them. No worries. Right, and so those outliers really affect the mean and the standard deviation. Yeah.
So just to make sure that I'm understanding this correctly, it's like another way to say that they're resilient to outliers because they don't change as a result of outliers being added into the data.
You know what? That's a more pleasant way of saying it. We use robust as a term, but I think resilient works as well. Right. And so now let me scroll back because I don't know. I don't know where 10 million would fall on this. I'd have to do my scientific notation work. But what happens, luckily we have these calculated already. So what we're talking about are robust statistics or resilient. Right, and so what we know is the median and interquartile range are robust to outliers, while the mean is always pulled in the direction of the outliers. So it's not robust. While the mean is pulled in the direction of the outliers, potentially more than one. Which means what? Graphically, it means that it's pulled in the direction of the tail, right? Wait, that sounds familiar though. I know, right? Crazy. So it's skewed in the direction where the mean is going to. It's almost by design. I'll say in the direction of the tail. Right. Okay. So if we just look at the numbers, we don't need to see, but what we would expect given this distribution, right? If I'm looking at the mean versus the median, I would expect the median to be somewhere in the lump here, just kind of hanging out, usually around the mode, right? And I would expect the mean to be slightly higher, right? With this skew in the positive direction or the right skew. So if we look at the original data, first off, the median is 190 and the mean is 245. So that checks out, right? The mean is higher than the median in this case, which is what I was expecting from looking at that distribution, right? The interquartile range is 200. The standard deviation is 226. Those are hard to wrap our heads around. I think measures of center or a spread are kind of hard to think about, right? Interquartile range is fine. It's the distance between where that covers the central 50%. Standard deviation, not so much. It's hard to kind of think about. So now for the spreads, I would say you just compare them relative to themselves as the data changes. So if you move the largest data point to $10 million, the median doesn't change. I'm not entirely sure why it would change. Maybe we're adding a data point. I don't know, whatever. Just accept it. So the median doesn't change, but all of a sudden the mean jumps from 245 to 309, right? So that's a big jump. Okay, so it's not robust to that outlier. I guess we're adding a data point, maybe. And then if I move the smallest to $10 million, the median changes ever so slightly, but the mean changes even more. I don't know, can't wrap my head around it. I think they're shifting the entire data set, whatever. The thing is, the mean and the median are used in different scenarios, right? So if you have skewed data, then you should be using the median and the interquartile range as your measures of center and spread, right? And so if your data is skewed, skewed data, then you use the median and the interquartile range. Whereas if you have unimodal symmetric data, so a normal distribution, we're not calling it that yet, but we will, right? And so here, if it's unimodal and roughly symmetric, then we can, that was a mess. Symmetric, well, it's all a mess. Then we can use the mean and the standard deviation as the measure of center and spread. And I'll write normal distribution because it's a name. I like to capitalize it to emphasize that it's a name. Otherwise it gets confusing. Right, so why wouldn't we just use the median and the interquartile range always if it's going to be more robust? Well, there's a whole toolkit that we get to use if we can apply the mean and the standard deviation instead, right? So we're hoping for that normal distribution because we know how to deal with that, and we have all these tools that we're about to bust out. But that's why it's important to know the shape, because sometimes when you apply the mean and the standard deviation, right, we can always calculate the mean and the standard deviation. As you can see here, you will get numbers, right? But that's where the human element comes in and says, well, I shouldn't be using these, right? Well, this is just what I said, but in a slide. So let's see here, the median and the interquartile range are more robust to skewness and outliers than mean and standard deviation. There it is. And for skewed distributions, we use the median and the interquartile range. And for symmetric distributions, we use the mean and the standard deviation. Recap. So here's a little question. If you want to estimate the typical household income for a student, would you be more interested in the mean or the median income? Remembering that anytime there's money involved, it's typically skewed, right? Especially things like household income, that kind of thing. So it touches on a couple of things. One, what's the expected distribution? Two, given the distribution that you're expecting, right? Is it skewed or is it? Right, given the distribution that you're expecting it to be, then what's the appropriate measure of center and spread, right? So it's a twofold question. Now, what I would expect to see is maybe something like this, right? I would expect to see that as my distribution. This is skewed, right? And so then I should be using, since it is likely a skewed distribution, I would use the median. Which brings me back to, when you hear on the radio the average home prices and things like that, we shouldn't be doing that, right? Because that's a skewed distribution, but it's pretty rare that they talk about the median, but they should be, right? So you'll hear it now. Maybe people don't listen to I listen to the radio on the way to work. But that's the only time, I guess. And home counts too. You'll hear it, you'll see it. So if we think about the relationship between the mean and the median, just remembering that the mean is going to be pulled in the direction of the tail. Okay. Then if the distribution is roughly symmetric, right, then the mean and the median and the mode are all basically the same. Okay. And so I only throw the mode in there because it's what people talk about. So, oh, I did a stats class once. Oh, really? Yeah. Yeah, mean, median, mode, that kind of thing. Yeah, that's a thing for sure. But the mode is just the peak, right? So all the mean and the median are all roughly in the same position. They don't have to be exactly the same, right? But roughly. Whereas if we have a skewed distribution, so something like this, right? That's a weird distribution to look at. It's still right skewed, it's multimodal looking, okay? But that's okay. So then the mean is going to be greater than the median, right? Because it's in color, but it's kind of hard to see. So here, the mean is here and the median is here. So they've obviously done the calculations. For emphasis, I probably would have put the mean somewhere around here, but obviously it's closer than that, but it's still pulled in the direction of the tail. So if I didn't have the values, I would have put it there. How about in the other direction, right? So again, here, the median is also being pulled a little bit, right? But not too bad compared to the mean. Oops. Come on. The mean pulled in the direction of the tail. I'll write a reminder here. Even though we've already written it, the mean is pulled in the direction of the tail. Nice. Okay, this one, I'll just zoom out a little bit. Here's the distribution of the percentage of time in class spent taking notes. We've got some low values here, some really high values, right? So most students, presumably, well, I feel like I'm taking notes the entire time. Well, I'm blabbing for sure the whole time. But which is most likely true for the distribution of the percentage of time actually spent taking notes in class versus on Facebook, Twitter? Weird choices, but things get outdated really quickly, I think, now. So first thing we're gonna do is we're gonna think about just the general distribution. If I had to describe the shape, I would say it's unimodal and it's skewed to the left, right? So here the shape is unimodal, right? One mode, but it's skewed left, right? Because I need to take like a Salto door course to figure out how to unlock the door. But now you're all trained to know that it's just locked. I have to untrain you. All right. So given the shape, right, I'm going to say the median would be somewhere around here, whereas the mean would be pulled in the direction of the tail. So it would be over here, maybe. I'm just drawing these lines just somewhat arbitrarily. Right. So that means that the mean would be less than the median. Is there such an option? Oh my gosh, there is. If we have extremely skewed data in this kind of scenario where it's really, really hard to see the distribution because it's basically all just in one stack, right? And then we've got these very, very small piles stretching all the way out, right? If those weren't there, then we could break this up more and see more, right? But one of the things that we would do here is apply a transformation so we can transform the data. And a common one for skewed distributions is to do a log transform. Now in stats, the only log that exists is the log base E, so the natural log. Okay. And so here, which gets confusing because I usually just write log, but I mean log base E. So here, if we take the log base E is really what it is. Or I'm not going to worry too much about it, but this is log base E or ln, the natural log. It's not something that we're going to be working with, so I'm not too concerned. But what happens to the distribution? Now all of a sudden we can see better what's going on. What's the problem? The problem is I have to communicate to my client in terms of log base E. Oh, well, I took the natural log of the number of basketball games attended. That's really hard to communicate, right? And so for me, that's one of the reasons I try not to do any transformations because interpretation becomes really difficult, right? And so, and I think there's okay, pros and cons of transformations. Okay. And so skewed data are easier to model, of course, right? We can see now the distribution. And this actually should be, pretty sure this is the log base E of the games. Okay. Can't be number of games, that doesn't make sense. Little typo. Yeah. But what happens is the results here might be difficult to interpret because talking about the log is pretty meaningless to most people. All right. So we've already talked about it, but what are some other variables that you just expect to be skewed and that you would, if you run into trouble visualizing the distribution, try a transformation for? And that would be any sort of money data, right? Income, household sales, that kind of thing. And so, oh, I like to do orange, I think. I was gonna say any, but I'm gonna say most. Most variables involving money. Right, things like income, sales, that kind of thing. You get the idea. Money. Time is it? 12:10. Okay. Whenever I present it, puts it in blackout mode, so I can't see the time. It's really inconvenient. Okay. The last thing I just want to show you is this intensity map. There's nothing more I want to say, but it's just another way to visualize numerical data. Okay. And so here is another way to visualize numerical data. Of course, you have to have map points to map them to, physical map. Sometimes it's truly a map, right? Sometimes it's a kind of a heat map, right? Heat maps were all the rage in data viz like 10 years ago. There's all heat maps everywhere. And then we moved on to kind of moving bubble charts. I don't know what we're doing now, but right. And so the change in the population, if it's really, really dark, it had over 20%, 10 to 20, 0 to 10, 0 to -10, -10 to -20, and over 20% decline. Wait, that was a little mashup, right? And so here looks like central United States had quite a decline, whereas the coasts generally saw increase. All right. We'll end there because we'll start categorical data next day. So that's the end of numerical data. Any questions before we call it? All right. Then I'll see you on Wednesday. Oops.